So today we're starting with video lecture 1 for chapter 5. We're going to look more in depth at the electron's role in an atom. We know the periodic table is divided into vertical columns called groups. And the significance of the groups in the periodic table is that they represent what we call the valence electrons. The valence electrons are the outer electrons in an element. These valence electrons are represented in what's called a Bohr model. So we find electrons a specific distance from the nucleus in a specific shell. The shells can hold a certain number of electrons. So the shell number squared times 2 is the maximum number of electrons. So the first shell, if we take 1 and we square it, that's 1 times 2. The first shell can hold 2 electrons. The second shell, so 2 squared is 4 times 2, can hold 8 electrons. The third shell, 3 squared is 9 times 2, can hold 18 electrons. And what do you think about the fourth? So 4 squared is 16 times 2 is 32. So we need to know 2, 8, 18, 32 for the number of electrons that a shell can hold. So draw the Bohr model for fluorine and chlorine. We start with our nucleus, and then we start building shells. Fluorine is atomic number 9. You should have your periodic table out to look this up. So we have to take the 9 electrons and distribute them in orbits or shells. And we see that the first shell can hold a total of 2 electrons. We need to distribute 9, so there's 7 left. And what we tend to do is to go around in a circle. There's 4 of the 7, and then 5, 6, 7. So that's the Bohr model for fluorine. Chlorine is atomic number 17. So we draw our nucleus. Then the first shell can hold 2 electrons. The second shell can hold 8 electrons. So that takes care of 10. So we have 7 more to distribute. And we will put them into the third shell. So 1, 2, 3, 4, 5, 6, 7. And there you have it. That's how we build Bohr models. Any element in group 1 will have 1 valence electron. Any element in group 2 will have 2 valence electrons. So we're seeing a pattern. If we skip the transition elements and go over to group 13, which starts with boron, drop the ene, and that will tell you the number of valence electrons. So group 13 is 3 valence electrons. 14 is 4, 5, 6, 7. And any element in group 18 has 8 valence electrons, except for helium, which if we look at the reference table, the periodic table, only has 2 valence electrons. Electrons closest to the nucleus have the lowest energy, and as you move away from the nucleus, the electrons pick up energy and will have the highest energy. If you think about running a race, who has the advantage? The person running the inside track or the person running the outside track? And obviously it's the inside track. So the person in the outside track has to travel faster, has to have more energy in order to keep up So the farther you are from the nucleus, the more energy the electron has. In the ground state, the electrons are in the lowest energy level available. This is how we normally draw a Bohr diagram. In the excited state, an electron has absorbed energy, either through electricity or heat, somehow, and they move to a farther out energy level. That's an unstable configuration, and when they fall back down, the electron gives off the energy it's absorbed as light. So a hydrogen electron can absorb energy and move out, and then it falls back down. It can absorb more energy, but then it falls back down. It can absorb a lot of energy, and then it falls back down. So those are all things that an electron can do. If an electron absorbs enough energy, it can leave the atom itself. And this is what we call being ionized. Hydrogen's atomic number 1, so it has 1 electron. In the excited state, the electron can absorb energy and move to a farther out shell. So this could be a possible excited state where it jumps out a shell. Next, we're going to discuss the spectrum of visible light. I have a video to show this at the end of this lecture, but it basically talks about how the electromagnetic spectrum can be broken down into different wavelengths, from shortwave and AM to gamma rays. But the important thing to notice is that visible light is only a very, very small part of the electromagnetic spectrum. If we take visible light and we put it through a spectrum, we get the colors of the rainbow. But if we take an element that is burning and we put it through a spectrum, we don't get a rainbow. Instead, we get these individual lines. And these lines are the signature of that specific atom. Lithium will always look like this in terms of a Berthollet spectrum. It will have some green line, a kind of yellowish line, and then an orange, and maybe a little bit of a red line. It will always be lithium that shows this signature. So we can identify an unknown by matching it up with known bright line spectrum. So here we have a mixture. What elements could be in that mixture? So we have to match up these lines here with something above. And I can see that these 3 lines match up with strontium. So wherever strontium is, there's going to be these 3 lines. So one of the elements is strontium. What other element matches up with this unknown? And I can see that this one does match up here. So the other unknown is lithium. So we'll practice this in class, but this is something that the Regents does ask you about. So that's going to be it for me, and a short video to follow on the electromagnetic spectrum, and then that is it for today. So have a great day, and we'll see you in class.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
For thousands of how-to and advice videos on any topic, visit monkeysee.com.